कारण ते मी जसं म्हणलं ना मला पण डायरेक्ट नाही करता आलं त्या गोष्टी पण हे चालू होते ना आपलं सोर्स. हो मलाही तसं सांगितलं ना डायरेक्ट देत नाही ना इव्हॅल्युएट करतात सगळं. हो 3 झाले. हम्म. 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 नाही. नाही पण ते आउटकम मला मिळालं नाही ना. मला मिळालं नाही ना सगळं तुम्हाला मला मला सॅटिस्फॅक्शन कधी झालं असतं माहिती का तुम्ही आले असते तर एवढे एफर्ट्स घेतले तुम्ही सगळं व्यवस्थित पटवून. बरं ऐका ना नंतर बोला पण FDP चालू करायचं मला. ठीक ठीक. ॲडमिट करून चालू करा मग सगळं. हां करू दे ॲडमिट. तुमचं लॅपटॉप आणलं नाही ना. बसा बसा तुम्ही चालू केलं का मीटिंग चालू केली का. हां ॲडमिट करा. प्रशांत जॉईन झाला का.
टोटल 23-24 झालं. 27 झालं.
प्रशांत काय का बघा आणि यूट्यूबचं काय स्ट्रीमिंग बोलणं चालू जातं. ऐका ना यूट्यूब स्ट्रीमिंग झालं होतं का. पाठवते मला पाठव. जाऊ लवकर. कुठून येईल तुम्हाला? चालू करा मीटिंग चालू करा. हा इथूनच चालू करा. चालू आहे.
Okay, can we get started?
Welcome all of you. Welcome all of you for the day 3 of FDP of Harnessing Intelligence Deep Dive into Machine Learning. Now I request Prashant sir to present for the.
All right. Thank you. I will start with sharing my screen. All right. So yesterday we covered a couple of supervised learning algorithms like linear and logistic regression. Essentially, they were linear models, right? So one was used for regression, so to predict value, to predict numerical continuous values, and the other one was a classifier, which was used to classify the data into fraud or non-fraud or any number of classes, right? So that was logistic regression, and the other one was linear. So today we are going to move on with um, other supervised machine learning algorithms. One most commonly used uh, classifier is a tree-based classifier, which is also called as a decision tree. And to start with, we will start with the decision tree today, the decision tree classifier. So the basic idea of a decision tree is that you ask a question. Starting from the root node, you're asking a question to the decision tree, to that tree. And based on what answer you get back from the tree, you're trying to classify the data. And then sequentially you start moving forward, like further down the tree, and finally you reach the bottom of the tree, which are also called as the leaf nodes. So these nodes that you see here, these are called the leaf nodes. Once you reach the leaf node, this is the place where you kind of come to the decision that, okay, what class does this particular data point belong to? So by class, I mean it could be anything. So for example, it could be whether a tumor is benign or malignant, right? That could be that could be a classification. Then that could be our regular fraud or non-fraud. So these are all types of classes that you could have within the data set. You could have more than two classes as well. So if you're classifying a flower based on what type of flower is it, so that could have n classes within that data set. Essentially, what we're trying to do, start from the root node and trickle down to the bottom by asking questions to the tree at each node. So if you look at this example over here, right, what we're doing is we are asking. So for example, let's say heart rate is one of the features in our data set. So what we are doing is we are asking the tree. This is the root node. This is where the tree starts. So we are asking the question to the tree that is the heart rate greater than 100 beats per minute, right? Is it greater than 100 BPM? If it says true, then in our data set for that particular data point. So for example, if the data set consists of a table which stores a patient's information, right? So one row corresponds to a certain patient's information. So let's say patient 1 has a heart rate of 100. Let's say patient 1 has a heart rate of 120, right? Patient 2 has a heart rate of 80. So what happens is when patient 1's data point comes into the tree for classification, it will go, it is true, right? So it will go to this side of the tree, and then it will be evaluated further down that branch. And so here you can see that the recommended action for this patient is go see a doctor. And if it is 80, it will go to the false branch, and further on it says no worries, okay, you're good. So this is a very simple way in which a tree is making decisions, right? And so this is so if we try to look further into this, for example, here we have heart rate, right? Similarly, we could have something like if once we classify the heart rate. So for example, now this guy was 120, so he went on this route. The other guy was 80, so he went on this route, correct? So now further, when we come to the next level of the tree, we could have something like, say, weight, right? So if weight of this person, if the person has a 120 heart rate, further, if the weight of the person is greater than, say, 100, or there is a condition here that, okay, we ask the question again. So next step is, again, at the second level of the tree, we are asking the question. So let's ask if the weight is greater than 100 or not. So if weight is greater than 100, we go down this branch, right, on the right branch. And if it is not, then we go down the left branch. So, and then further we classify. If it is less than 100, let's say that no problem. Okay, so that's fine. So this is the action, and this is what we classify this data point into. Let's say this patient has no problem, but if the weight is greater than 100, so let's say weight is 120, we then move to the next. We move to the next branch in the tree, so next level, and here we might have something like what is the BMI, right? BMI of that person, and then if we say that BMI is above 30, then go here, and if BMI is less than 30, then go here, and then finally these are our leaf nodes where we make the final classification. So let's say BMI of this patient is 32, the patient lands in this box, so we'll say that okay, go to doctor. So that's the category that we classified in. And if the person has less than 30, let's say 28, then here we say that okay, you are fine, no problem, something like that, So this is what a decision tree classifier looks like. So what happens is you start from the root node, and you at each level you have different features which have conditions. So you will ask those feature nodes questions of what is the value above or below a certain threshold, and if it is below a threshold, you go down a certain path. If it is above a threshold, you go down another path. And so this is a high level overview of how decision tree makes its decisions. Now we want to understand how is this tree actually created, right? So let's start with some basic ideas. Like the idea of a decision tree is to start from the top and work your way down to the bottom of the tree. And once you reach the bottom, the last level of the tree, essentially you will get the decision. Whatever class that you are trying to classify the data into, you will find that. When you cannot break down any further, so that is the point. So at a point where you can't go any further down in the tree, that's your classification point. Now, some terminologies to know is, first is the root node. So the point from where the tree is starting. So basically, if this is the tree, then the origin is the root node. So that's called the root node. Nodes that are inside the tree and are connected to other nodes. So nodes like these are called internal nodes. And nodes at the edges of the tree, which do not have any further child, like these nodes, right? These are called leaf nodes. So this is just some terminology to know when we talk about decision trees. Moving on. Now, how do we create a decision tree from raw data? So to start with, and this is the example of a raw data set, like I was talking earlier about patient data set, right? So whether a person has chest pain or not, whether the person has good blood circulation, whether the person has blocked arteries. So these could be your input variables, and based on these, we could predict whether the person has heart disease or not. And essentially, what you can do this by creating a decision tree, and then starting from the root node and then going all the way down the tree. So let's look at the process of how this tree is created. So we will start. We'll in the beginning we'll try to find a feature that should be at the root node. So we have to start at some point, right? So what should be the feature at the root node? Yeah, in this example, you saw that we had heart rate over here. So at root node, we considered heart rate. But why did we choose heart rate? There is a reason we chose heart rate. And how do you get to that feature? So what you see is we try to see how each of these variables are separating the target. So how much variance are they adding up to the target? So what we see is if a certain feature is not able to correctly classify a certain is not able to correctly classify the target, it is called as impure feature. So if there is a certain feature, let's say good blood circulation, it is not it is not able to predict the target as well as say chest pain and blocked arteries. So we would say that this is a relatively impure feature, right? While the other ones are relatively more pure. So they have lesser impurities. Now, how do you calculate impurity of a feature? Right? We have this metric called the Gini index, and Gini index essentially what you're doing is you calculating for this example, for the heart rate example, you are doing one minus the probability of yes square, like for in within that within for that particular feature, how many of these how many of the total number of nodes are yes square minus how many of the total number what is the probability of the total number of nodes being no, and then square it and then subtract it from 1. That gives you your Gini index for that particular feature, right? So it is calculated for each of the leaf nodes. Now, this is for this example, but in general, when you are trying to calculate the Gini index of a certain node, it is essentially 1 minus, if you say you have C classes, right? So you can say the probability of predicting that particular class. So in this case, heart rate, within how much is the probability of that feature predicting your target class, and then based on that you calculate this value, and this is your impurity for that feature. Now you want, after you calculate this impurity, this value, once you calculate for all the available features in the data set, you choose the one with the least Gini index as so once you calculate the Gini index, you take the weighted averages. So this essentially, once you calculate this, right, you take the feature with the least Gini index, since that would be the least impure feature, right? And that feature would serve as your root node, and then you move on from there. So you calculate further. So now we know that how we get the root node. We calculate the total impurities for each of the features in the data set, and then we choose the one with minimum impurity as our root node. Now, one thing to understand here is, so we have chosen the root node, which in this case, let's say, is the heart rate. But now we have to calculate further also, right? So we have to see what our, once we have the root node, what should the leaf nodes be? So what should the leaf nodes be? Which feature should we consider at leaf nodes, so that we are making more precise predictions. So in case of so for example, let's say we have 100 patients, right? And we say that if heart rate is greater than, let's say, 80, right? If heart rate is greater than 80, you go here this side, and if heart rate is less than 80, you go this side. Now, if 70 of these patients go on this side, and let's say 30 of these 100 initial patients go on this side. So now we need to do further classification of these patients, right? Like how can we further roll out the tree and create in the end create the whole tree. So to do that, we will now have to find how well the other features are explaining the data. So now we will move forward, we'll calculate the total impurities for each of the remaining features. So in this case, you have chest pain and blocked arteries. These are the two remaining features, and we will be calculating this in the same way that we calculated Gini index. In this case, we will do the same for other features, starting from this node, right? And similarly, once you calculate the features, right, you further split the tree down, and then for each level you keep on doing that. I will explain how. I'll with an example I'll explain, so it will be clearer, like what I'm trying to say here. But what is happening is you're essentially splitting the data at each level based on the calculated impurity from rest of the features. And once you get that impurity calculated, so for example, let's say here the calculated Gini impurity at this level, at this node is 0.6, right? Now then, at this level you got 0.5, and here you got, let's say, 0.2. So you split the node and you came to this level, and now from here you will split it further. But one thing to understand here is that uh, if the Gini index of a certain node, right? So if of this, let's say for example, let's consider this node. Let's say we got a Gini index of 0.1 here, which let's say it's very low, right? So after this point, once I'm doing, even after doing the splits, after I did the split, I calculated impurities for rest of the features. So let's say blocked arteries, I calculate the Gini index, and I find that at this point the Gini index is 0.4, and at after splitting it the other way, the Gini index is, let's say, 0.3. So basically splitting has increased my impurity in the data set. So what we do is, after this point, we don't go further. We stop rolling out the tree. So we prune out the tree at this point. So this is the point that we reach, right? And this is where your tree ends. And once you reach this point, basically the prediction that you're trying to make, for example, let's say 100 out of 100 patients, initial 100 patients, good, let's say these guys do not have good blood circulations, and the people going down this path have good blood circulation, right? Now we reach this point. Out of 100, let's say 30 people have come here, right? Now out of these 30, let's say what we are trying to classify is whether a person has a heart condition or not. So whether he has a heart condition or does not have a heart condition, right? This is our final classification that we're trying to make. So now let's say this is our leaf node. Ignore this part. Ignore the rest of this. So because the Gini index at this level is higher, and so we stopped rolling out the tree at this point. So we reached this point. It says so chest pain is yes, and 30 people have come from our training data. 30 people have reached this point. Now we know the true labels of the data, right? Because it's supervised learning. We know that out of these, let's say out of these 30 in our training data set, 20 had a heart condition and 10 didn't have a heart condition. So once a node, and once you get a new node, for example, at the time of inference, when you're testing your tree, what happens is, first you ask the question, okay, does the person have a good blood circulation or bad? You say, okay, this new data point that we are trying to evaluate, it has, let's say the person does not has good blood circulation, let's say. So it comes to this side. So, and then on chest pain, so how do we evaluate this? Since this is the terminal node, this is the terminal node in the tree. This data point, the new data point, is assigned the class of the majority class in this terminal node. I hope this is making sense. So basically, since this chest pain node during our training process is the terminal node in the tree, so this is the leaf node, and it had 20 people categorized as having a heart condition and 10 people as not having a heart condition. Any person who lands in this node, right, will be categorized under having a heart condition, because that is the majority node, majority class for this node during training. So that's how we That's how we classify. So once you try to split the data, if you are not able to split it further, you stop rolling out your tree at this point, and the class of, and whatever class is the majority class at that node from your training data is given. So that node is given that label. Okay, so that is how decision trees work, and that is how decision trees are rolled out. So um, another thing to know is that if a feature is numerical, what we so if one important thing is how do you split, right? So how do you decide that if heart rate is greater than 100? So how do you come to the value 100, right? Well, you can we know how we chose heart rate, because heart rate we got from the Gini index. So the least amount of impurity was in that heart rate feature. That's why we chose it as the root node, and that becomes our root feature, let's say. Now, but how do we decide the threshold? What threshold to choose from, right? So how do we come to come to value 100? To do that, we basically just sort the data. If the feature is numerical, we sort the data out from, so we get a range of the complete feature. So like maybe heart rate is ranging from 30 to 120, or maybe even 200 actually. So this is the range of that heart rate data, right? So what we do is we break the data down into multiple ranges, and we take averages of each range, and those we consider as thresholds, and then we try the splits. So once we will try to do it for, let's say first range is 30 to 50. So let's say threshold we consider as 40. So first split we'll try to make at 40 in our tree. So if with the root node here, we'll make the first split at 40. If greater than 40, go this way. If 1 second, let me just, yeah. So if greater than 40, go this way. If less than 40, go this way, right? So this is one split that you do. So once you do the split, you calculate the Gini index for the child nodes. Okay. Now what you do is you change the threshold to, let's say, 60 now, based on whatever range you have for that numerical variable. So this way you keep on trying different thresholds until you find the threshold that is giving you the optimal Gini index, and based on that optimal Gini index for your child nodes, and that is the value of threshold that you maintain and continue further down the tree. So once you find that optimal threshold, you go to the next level of the tree and then continue the same process until you roll out the full tree, right? So for numerical data, thresholds can be calculated this way, because it's a continuous value. You wouldn't know basically what should be your threshold. But for categorical data, it is easy, because it is yes no type of a thing, right? So as we saw here, for categorical data, it's pretty easy. If it's no, what to do. If it's yes, what to do. So threshold calculation for categorical is, you just straight away consider that data point, and uh, you consider each category and split based on each category. You see what split is causing the least amount of impurity, and then roll out further. So that is how decision trees work. Now, what I will try to do is, now that I have stated the whole algorithm down, I will try to give you an example of how this thing works. So let me just get a blank page. Okay, so we have a blank page now, and here let's first start with let me just write down what Gini index was, right? So Gini for a given node was your 1 minus the sum of all the probabilities, right? For each of these classes that we have, right? So now let's say, now how do we calculate the Gini impurity for a certain node? Now, let's say there are, so there is a node, right? And there are 10, and for this particular, and we are trying to classify a certain feature. Let's say the feature is X. For this node, we are trying to calculate the impurity, and there are three classes A, B, and C. X could take these values, right? So your X could essentially take all these values. Now, what we are trying to do is, let's say there are 10 nodes at this node. So there are 10 data points at this node. Out of these 10, let's say 4 belong to A. So 4 belong to A, 3 belong to B, and 3 belong to C, let's say. Okay. So now, what is the probability that we get node A? What is the probability that one of the node that I sample from these 10 nodes is A? It's easy, 0.4. For this, it is going to be 0.3. For this, it is again going to be 0.3, right? And now, how do I calculate the Gini impurity from this point? I will simply substitute it in this formula, which is again 1 minus, let's say, 1 minus my probability of A plus probability of B square plus probability of C square, right? And that will, essentially, what does that come to? Let's see. Now this will come to 0.16 plus 0.09 plus 0.09. That is, this is 34, I think, and which will give me 66. So this becomes my Gini impurity. So this becomes my Gini impurity for this particular node, right? So this is how we calculate the impurity value, right? Now we move further. So now let's, and this what we calculated for X, you might have other features like say X1, X2, X3, you might have N features. You calculate this in a very similar way that we calculated this, you calculate it for all the features. And you choose that node as your root node, which has minimum value of this. Once you do this calculation, the feature that has the minimum value will be chosen as your root node feature. So let's say for this particular case, we have X1, right? So now from here, how do you get your child nodes, right? So so now you have the root node. X is your root node, right? So from here, you want what should be your child node. So let's say after, okay. So here you have X. After this, you have a child number 1 and child number 2. These two nodes you are trying to form, right? But now you want to find some threshold T at which your X node can be classified. Now let's say X is a real number, right? So you want to classify, you want to find some threshold T for which you can classify this node, right? So let's say for child 1, we say, this eraser starts randomly. Okay, one second. Yeah. So let's say for class of we'll say then or equal to the threshold, right? And let's say on this path, out of the total 10 data points, 6 came this side, right? And 4 came this side when I chose the threshold T. Okay, when I chose T as the threshold, 6 of these data points came this side, 4 of these came this side, right? So now let's do that calculation for child 1. Out of these 6 that came here, let's say A has 3 of them, B has 2 of them, and C has 1 of them. Okay. So This side we have 6, 3A, 2 are B, and C, 1 is C. So now similarly that we did at the time of root node, we do the probability calculation, right? So let's say P of A, probability of having A is 3 by 6 here, which is again 0.5. For probability of B is 2 by 6.33, and probability of C is 1 by 6, right? So that will be 0.17. Okay. Now, similarly, I can calculate the Gini index for this child node, right? For C1. That is 1 minus what I got here, 0.5 square plus 0.33 square plus 0.17 square, right? And this will come to something 0.2 probably something like something close to 0.6. Okay, once you subtract it by so 0.4, yeah, it will probably come somewhere close to 0.6. So this will be the Gini index of your child 1. Similarly, let's say let's take child 2 for this particular threshold, for this value of t. Now we do the same calculation for child 2 where x is greater than t, right? Now here we got 4 data points. Out of this, let's say A has 1, B has 1, and C has 2, right? So similarly, we get probability of A as 0.25, B is also 0.25, 0.25, and C in this case is 0.5. Very similar way as we calculated Gini index before, we calculate Gini index in this case again, right? So 1 minus 0.25 square plus 0.25 square and 0.5 square, right? So whatever you get, 0.6, 0.06, 0.06, 0.25 subtract minus 1. Again, this is close to 0.6 something. This is also going to be closer to 0.6, right? Now this is how you got your Gini index for each class, right? So this after doing this, you take you take the total weighted combination of both these. So basically you got 0.6 for this, right? So 0.6 for this for child 1 and 0.6 for, let's say, child 2 as well. So what you do is since 6 of these out of 10 have come on this side, so a weighted sum of both these indexes would be 0.6 out of, so 6 on 10 is 0.6 into the Gini score that you got, 0.6 plus 0.4 into 0.6, right? And that will be your cumulative Gini index for this particular threshold, right? Now what you want to do is you want to change the threshold to something else. Now let's say my first threshold that I took was T1. Now I change it to T2. I take a new value and I calculate the same thing again, and I see if I can get a lesser impurity. Uh, uh, and then I do this for all possible threshold values, and in the end, I will find the optimal threshold is the one that is minimizing this value, the combined the weighted Gini index, right? So that's how these decision trees work. I hope this example was helpful in explaining the computation that goes on in the back end when we are calculating decision trees. One thing to understand is that splitting is an expensive operation. So multiple strategies are used. Like I told you earlier that in numerical features, we are splitting the features into we are sorting the range of the features. For example, for heart rate, we took it from 20 to 200, right? And then we split it into multiple ranges. We take average of that range, whatever ranges you split it into, and then that average is taken as threshold, right? So that average is taken as the threshold, and similarly for different, so you don't have to calculate the Gini index for 20, 21, 22, 23, 20. No, so you can take averages at certain splits, and then you can narrow down to the best threshold within that numerical range, right? Also, there is some research in using custom heuristics for doing feature selection. So for selecting the threshold, you could have some, using your domain knowledge, you could create some kind of a statistic that you could use to find the threshold within the data set. And also there is another thing which is called pre-pruning. To save computation, what we do is one thing we said was, we discussed earlier, was once the impurity value is less than your child's impurity, right? So when node impurity is less than your child impurity, you will say that, okay, stop rolling out the tree. One more thing that you can do is, rather than going to evaluate child's Gini impurity, you could simply set a threshold that, okay, if this impurity turns out to be less than 0.1, I want to stop the process. I want to stop for going to the next level. This will be my leaf node then. So this is one strategy that is used to save computation. So you decide thresholds for impurity. If the impurity goes below that threshold, you don't further split the tree. Okay. And another thing is that if a node has, let's say, in the example that we discussed earlier, that node had 10 distinct data points that came, and 6 of them went one side, 4 of them went the other side, right? So imagine if only one of them came this side, only 9 of them went this side, only one of them came this side. So if only one is coming this side from the training data, it doesn't really make sense to split this even further, because we know that the class of this node is going to define this particular node. So this data point is going to define this node. So then another condition that we use for terminating the rollout of a decision tree is that if the number of data points at a given node goes lesser than a certain threshold, then also you can stop the creation of the tree. Now this what I'm saying is, all these points that I'm making right now are how you can optimize all the computation process, right? You can save compute by using these hacks when you're actually implementing a decision tree. And also the third one is, again, if the depth of the decision tree again goes more than a certain value, maybe more than your number of features, then stop rolling out the tree, right? So that is another thing. So depth should always be less than the threshold. So these are some things that we can keep in mind while we are calculating, while we are actually implementing a decision tree. Another thing that we need to know, like keep in mind about decision trees, is that in general they are binary trees. As you know, as you can see, we are splitting it into two distinct nodes using some threshold, right? So if you're using one threshold, then it will be split into two distinct branches. So this is going to be a binary tree. But it is possible that there are some cases in which it is called a multi-way decision tree. So you could have 3 branches. So for a numerical feature, you could have multiple thresholds. So you could have multiple conditions within the threshold, and so you could go via each branch. The overall process remains the same. This method is used quite often conventionally, but yeah, just to just to put it out there, that's multi-way decision trees are also a thing. Now, okay, one more thing that I want to talk about is we talked about decision tree as a classifier as of now, right? So whether a person has a heart condition or does not have a heart condition, no heart condition, right? So this is a classifier. We are trying to classify the data, that what particular class does that one particular data point fall into. But you could also you could also use a decision tree as a regressor. So what do I mean by a regressor? Um, so here we are predicting a class, but we could also use decision tree to predict a value, right? So what we do is instead of using Gini impurity, we use the mean squared error between for certain threshold values. But like the process remains the same, but now we, instead of calculating Gini impurity, we calculate mean square error. Then we roll out the tree again, and then at the leaf nodes, whatever data points you have, right, uh, you will the final value that you're predicting will be the average of these data points. So let's say this is your leaf node, and this has, let's say, 20, 50, 75, right? These are the final data points that got to this node during training. So now the average of this is 50. So this node, whenever a certain data point comes into the tree to be to run a regression on it, and if it comes down to this leaf node, the value returned by the tree is going to be 50, right? So this way, a decision tree can also be used as a regressor. Um, okay. So another thing about decision trees that I wanted to say was that it could very well overfit the data. Okay, so we need to be very careful while we implement these algorithms, because a decision tree could overfit the data uh, because it can easily make so many splits that it fits the data set perfectly. So we don't want that. So that's why usually decision trees are used as a combination, like at a given time we don't just use one decision tree. We maybe roll out 50 different decision trees, and then we take average of those 50 decisions, and that becomes our final decision. Now that this whole algorithm, it's a whole machine learning algorithm by itself, which is called random forest. um, and it has some further nitty-gritties which I'm not going to go into for now, but essentially in random forest you roll out 50 trees, and then you take the average, like n number of trees, and then you take the average of the decisions made by each tree to come up to your final conclusion. So that also kind of avoids overfitting the data as well. So yeah, with that I will stop with the decision trees for now, and we will move to the next algorithm, which is which is k nearest neighbors, which is a very simple algorithm used for classification, right? So in this algorithm, you don't even have to train your model or anything. What you need to do is just you have your data set, right? It's What we do is we simply take our data set, we plot it on n dimensional space. So as you can see here, you know, you let's say we have 10 different classes that you can see in this particular plot. Each of the classes is marked with a different color, right? What we do is uh, we simply plot those data points on in your n dimensional hyperspace, and then what we do is whenever you get a new data point, right? Let's say I have added a new data point over here. This is my new data point, right? Now I want to classify this data point. Now what, like, which out of these 10 classes does this data point fall into? It is what I will do is I will calculate I will first take top k nearest nodes from this neighbor, right? From this particular node. So what I'll do is I will calculate the distance of this particular node from my surrounding. I will calculate the distance from each node for from this newly added node. I will shortlist the top k shortest distances, right? Top k shortest distances. And from those top k, whatever class has the majority of nodes, I will assign this node that class. As simple as that. There's nothing else in k nearest neighbors. The only thing that we need to understand is how do you calculate the distance, right? So there you could use different types of distance metrics. One, it could be Euclidean distance, which is Euclidean is simply you can sum up the distances between each point that you have, right? So if you're calculating distance between, say, x and x dash, you could squares. It's the sum of squares, and then you take the root of the whole value, each of the dimensions, right? So that's your Euclidean distance. Then you have Manhattan distance, which is again the absolute magnitude. So if you have x and x dash for which you are calculating Manhattan distance, it is simply the magnitude of the difference between each of the dimensions. Sum it up. Minkowski distance, a little different. It uses a parameter called the order of the distance metric. But yeah, essentially it is similar to Manhattan distance, where you are calculating the magnitude, but also this the order of the distance metric, this parameter p, is used as a is used as an additional scale up factor for this distance. And there's another distance called Hamming distance, which is used for categorical classifications. So that is these are like some mainly used distances in k nearest neighbors algorithm. Apart from this, another thing maybe, okay, yeah. So how do you determine k, right? How do you say what is the best value of k that I should choose? Now that I have added this data point here, how do I know that I have to sample k? What is k? How do I find k? So what I can do is, in order to find k, what we can do is we can try different values of k, right? So first we can take 5, we can take 10, we can take 20, whatever. Like you can take different values of k, and you can find what is the one that is, once you start plotting the values, right, based on the classifications that you're making. So for what values of k is your accuracy the highest, right? So for each time you take different values of k, you will see that once you start plotting the accuracies, you will get something called as an elbow plot, right? It looks something like this, and there is this point of inflection where suddenly you see k dropping very sharply, and then suddenly you see it doesn't drop that much. So this point, at whatever k this drop kind of stabilizes a little bit, that is your optimal k. So this is called your elbow point, and you usually that k is chosen for your data. So that's how you choose k. Yeah, and that's pretty much everything that you need to know about k nearest neighbors. So very simple algorithm, no training involved, just calculate distances based on k, like take the top k nodes around the given node, and then within those top k nodes, whatever class appears the maximum number of times in that node is the class of your new node, right? Simple. Now the next thing that we are going to move to, the next algorithm that we are going to move to is called support vector machines. Now, support vector machines are also again highly effective method for very commonly used in shallow machine learning techniques. So, to start with, let's start with an understanding of how these things work, right? So, let's start with a simple one-dimensional classification that you can see in this case, right? Where you have a bunch of data points on belonging to class 1 on the left side, a bunch of data points belonging to class 2 on the right side, right? So now you want to separate this. You want to separate the two classes. How can you do that, right? You can choose some threshold value to separate. So let's say we choose this line, we draw this line. But then how do we know that this line that we have drawn between the two classes is the optimal line, right? How do we know that, okay, this is the right line that I want, this is the right threshold that I have chosen? So what I can do is, one thing that I can do is I can find the extreme edges of the two data sets, right? The extreme, of the two classes, the extreme edges, and then I can take midpoint of the two classes. So let's say this, right? Now this midpoint of the extreme edges will serve as my threshold, right? So this is fine. This works fine. I have the data clustered on both sides. I take the extremes and I classify the data based on the midpoint. Now, the one more terminology is that this point, this point, that is this line, this threshold, we call as margin, right? This is called as margin. Now, what we do is we try to maximize the margin, right? Because we took the extreme points over here and we took the midpoint. So this way you are maximizing the margin between the two classes. So that's why these are called maximal margin classifiers. Okay? Now they work very well if the data is clustered like this. You have blobs of data like this. But look at this example over here. Here, the data is not quite clustered, right? So one data point is over here, and then the rest of them are here. Now, if I try to do the same thing, if I take the extremes of each class and I draw a classifier over here, like I draw a threshold in the middle of those, this doesn't seem right, correct? It won't be able to classify the data efficiently. So now what we have to do here is we have to give some kind of some degree of freedom for this threshold, for this margin. So we have to give some relaxation. So we can say that, okay, let's say that this point we can ignore for now, and then we can choose these 2 points, and then based on that, again we choose the maximal margin classifier, right? So essentially what we are doing is what we learned in the first lecture. We are trying to achieve the bias variance trade-off. In order to avoid high bias, we are going to give some relaxation to your margin, right? So these are called as soft margins, so which allow some kind of misclassification, right? So that's why it's called a soft margin. And these kind of classifiers which allow some kind of a soft margin is called as a support vector classifier, right? So they are essential and they work pretty well in general when we have even higher dimensional data. Support vector classifiers, they work well, but then the issue comes. So okay, let's talk about this first. So once you have the support vector classifier, right? So how do you classify the data? So for example, when you have 2-dimensional data, as you can see in this particular example, your margin is a line, right? You are separating the two classes based on a line. And as you can see here, this is one of those misclassified data points, right? So, but still we are giving that relaxation, and so this becomes your margin in, so a line is your margin in 2D space. Now in 3D space, as you can see in this example, you essentially need to have a plane, right? This let's say this is a plane, and this plane is cutting your 3D space into upper quadrant, this part, and the lower side, right? So what this is giving you is uh, what this tells you is that in 3 dimensions, your margin is essentially a plane, and as you keep on increasing the dimensions, they turn into hyperplanes. uh, okay, so this is how support vector classifiers work. But now we there is another issue with these type of classifiers, the support vector classifiers, right? What happens if the data looks like this, right? So in this, you see there is one dimensional data. The classes are on C1, the class 1 is on either side of class 2. So if there is a lot of overlap over here, and I can't draw a line which is able to perfectly classify this, right? There is no way I can draw one line which can classify this data. That's not possible in this particular case. So my support vector classifier wouldn't really work in this case, right? Because I am not able to set one single threshold in this example. So that is where we go to the concept of a support vector machine. Now, what do we do in a support vector machine? Let me explain in a very simple way. So let's say this is one dimensional data, right? This you see here is one dimensional data. What I do is I simply plot the squares of each of these values, the squares of each of these values on y-axis, right? And then plot it. So this data I have basically projected it to a higher dimension. One dimensional data, I have projected it to a second dimension. So I get a curve like this, right? Where this is my x and this is my x square. So now if you see in 2-dimensional space, I can draw a line through this, right? And this could act as my classifier. So this will be able to classify my data very well. So this is called a support vector machine. So while classifying a new point, you can easily separate out the data by projecting it into a higher dimension. That's the idea of a support vector machine. The main idea behind an SVM is to start from a relatively low dimension, project your data to higher dimensions, and then use those projections to create your margins, and based on those margins you classify the data, right? Now how do you know what are you projecting? Like, for example, in this case, what I did was I told you that I am squaring the values, so I squared it and I projected to a higher dimension. But how do I know what values do I what function should I use to project to a higher dimension? So for in that case, I was using a polynomial function. So where, let's say the dimension that I was projecting it to was 2, because I am squaring it, right? So I am projecting it to one dimensional vector. I'm projecting it to a second dimension. Now, but that could be done to n dimensions, right? That can also be done, the projection can be made to n dimensions. So this kind of a function that can help you in projecting your data into higher dimensions, is called a kernel function, and is used by the SVM. Polynomial kernel that we used earlier polynomial kernel that we used earlier is a very commonly used kernel. Another one that is commonly used is called a radial basis kernel. So in polynomial kernel, you are projecting to the d-dimensional space, but in radial basis kernel, you are effectively projecting it to an infinite dimensional space. Now it is difficult to kind of visualize how a radial basis kernel works, but it behaves like a k nearest neighbor model where once you project the data, the closest points will have the most impact on your classification. The closest point to the to your current data point will have the closest impact on the classification, and the observations that are further apart, that are further away, will have a lesser impact on your classification. So that is what a radial basis function does. Another important thing to know in SVMs is once you have done, now that you know that okay, you are using a kernel function to project the data to a higher dimension, we are not actually transforming the data. When kernel function, what it allows us to do is it allows us to calculate the relationship between the two data points in a higher dimension. So it will allow you to calculate the dot product between two different data points in a higher dimension, but it does not actually project them in a higher dimension, right? So that is called a kernel trick. And and a kernel trick is the key way in which SVM saves computation. So if you actually try and project, so imagine having to project your d-dimensional data into infinite space using radial basis function, right? So if you're actually transforming the data into an infinite dimensional vector, like it's computationally it's impossible. So you don't really do that. You use the kernel trick to save a lot of computation. Now this is what the polynomial kernel looks like, where A is some feature x, B is another feature x dash, R in this case is your bias term, and you're projecting it to a d-dimensional space. Similarly for radial basis function, this gamma is the scaling value, as I told you earlier, that it kind of impacts as how much impact do your neighbors have on the current data point classification. That is decided by gamma. It's a scaling factor. And then A and B essentially are again just two features that you take and square them out. Now that is what the kernel trick does. What I'll do is I'll try to explain how kernel trick works. Maybe if I try to explain it mathematically, it might be clearer. So let's see. I will just take 5 extra minutes to explain this, why this is computationally efficient while we are using SVMs. Okay, so if we say we are using a kernel function for two variables, say x and x dash, right? And you want to project them on a higher dimensional space, let's say polynomial kernel, right? So polynomial kernel, I can write this as from this formula, right? I'm just putting this formula here. I can write it as, let's say my bias term for now is just 1, and I'm projecting it to d-dimensional space, right? So what this is doing is, instead of me having to project this data into a higher dimension, this kernel function will return to me the dot product of x and x dash in d-dimensional space. If I do this calculation, I don't really have to transform x and x dash into d-dimensional space, right? I could keep it in the same dimension that it was before, and I could use this function to the power of d to project this data into a d-dimensional space. And similarly for an RBF kernel, you are projecting it to an infinite dimensional space. Now, if we take an example, let's say you have two data points, right? Say was 2D data points, say 1 1 and 2 2, right? So these are your 2D data points that you have, and now I'm going to use your polynomial kernel, right? Kernel function. So what I can do is if I just apply this formula over here on these, so I'll have 1 into 2 plus 1 into 2 plus 1, and then I will, let's say I want to project it to three-dimensional space, right? So what I am essentially getting is 5 cube, just 125. So this, what is this? This is the dot product of these two in three-dimensional space. So I don't actually have to transform them further and then take the dot product. I can directly get the dot product. In this way, I am saving a lot of compute, right? And if I want to tell you about, maybe I shouldn't go into that. Okay, let's see. So so this is how you're saving computation, right? Now, how does the kernel trick work, right? So why does this kind of save, like how does this essentially project to a d-dimensional space, right? So how does an SVM use this, right? So what we do is SVM is aiming, so what we do with an SVM is we are trying to maximize our margin, right? We are trying to maximize the margin, and at the same time we are trying to minimize the classification error. So you can effectively see that it's a constraint optimization problem. So if the constraint here being that whatever the weights of the vector that I have, like the weight vector and the intercept, I'll talk about this, is we are effectively trying to optimize this, right? We are trying to minimize this. And while we try to minimize this, so where here W is basically your weight vector for that particular hyperplane, and B is your intercept value. So whatever hyperplane you are trying to calculate, the margin that you are trying to calculate, that will cut your data off, right? So that this is the weight vector for that, and B is the intercept, right? And what we are trying to do is we are trying to minimize this, right? And the constraint is that it should be greater than or equal to, it should be greater than or equal to 1, like this particular constraint, your hyperplane. So this is your hyperplane wx plus b into your classified class. So what this ensures is that all the positive class points, so which is greater than 1, so all your positive class points are at least 1 unit away from your boundary line, which is your margin, right? So this constraint optimization problem is kind of taking care of that. But now you see here, you see this w dot x, right? This is a dot product, and when you are projecting something into a higher dimensional space, taking a dot product is very expensive. So what in SVMs, what we do is we try to transform this this optimization problem, so this constraint optimization problem, into from one constraint, which was this was our constraint, right, that we had. So we are trying to convert it into a multi-constraint optimization. So we form a dual constraint. So by adding some Lagrangian multipliers to the existing optimization function. So if we do that, we kind of get a maximization problem, which essentially this is your Lagrangian multiplier alpha, and you are summing over the entire data set. But what I am essentially trying to say here is that these multipliers, you can ignore them for now. Like how they transform your initial uh, your your initial problem doesn't matter. But what happens is, once this is transformed to this, you can see here that this converts to this. So now here, instead of calculating the dot product, we have transformed this problem into calculating the kernel function, right? So now we move to other constraints. So now this is subject to what would this be? Your multiplier and your the sum over all your multipliers over your target variable should be 0. And the second is that the multiplier should always fall under, it should fall under under the range of the number of classes that you have. So that's you can ignore this part for now. What I'm trying to explain is, this is how the dot product is transformed into kernel function. And this is how this is why you save a lot of computation while training an SVM using the kernel trick. And this when you're trying to solve this multi-constraint optimization problem, you don't really use gradient descent because the gradient descent does not quite work well with constraint optimization. So here we use quadratic programming, which is another thing that you can take a look at. But I'm not going to go in the details of that for now, because it's kind of out of the scope of ML. So yeah, that is how SVMs work. Yeah, I think that's I think we can stop at this point. If anyone has any questions related to any of the algorithms that we discussed today, feel free to ask. Any questions? Okay, yeah. Is that the question? With SVM, is stock market prediction done? You could use it for that. But the thing is, for like we discussed of SVM as a classifier today, but yeah, it could also be used as a regressor. And if you're trying to predict the value of a particular stock, you could essentially also use an SVM. But I think for stock market, there are more like, it's more of a time series, multivariate time series analysis problem. So I mean, different, like people use different algorithms, and SVM could be one of them. Yeah. Any other questions?
Hi, Prashant. Pawan here.
Yeah.
This essentially can be used as detecting the phishing email or any fraud document.
Yes, you can, because you can use it as a classifier always. So, support vector machine, any of these algorithms that we discussed today, they can be used for phishing for fraud detection. Yeah. But usually, if you ask me, if you're trying to do fraud detection on industry data, what would work very well for you is to use some kind of an ensemble. So by ensemble, what I mean is, as I initially told you during decision trees, I'd also explained a little bit about random forest. So where you are rolling out hundreds of trees and then taking average of the decision, that algorithm, like these are called ensembles. So random forest is a bagging method there is another method called XGBoost, which also use multiple daisy chaining of decision trees, also works really well. So these you instead of trying a single decision tree, you might want to try ensembles on, and they really work well. So on these, if you see these Kaggle competitions, if you have heard of them, where they give you an open data set and you have to train an ML model which is performing the best. Usually, you will see that XGBoost and random forest algorithms are like the top performing ones.
Okay. Yeah.
Yeah.
Thank you, Bhushan.
Yeah. Any other questions? All right. So if you have any other questions, feel free to post on the group chat, and I can answer them. All right. Power sir, are you there? Can we stop for today?
If you don't have any participants don't have questions, then
No, I think yeah.
if anyone is having any query, just Prashant. Thank you.
All right. Thank you. If anyone has questions, you can post on the WhatsApp chat. Yeah. Thank you.
Thank you. Live streaming band karo. YouTube.
Thank you all for attending today's session. First of all, I want to thank Kadam sir for giving us very enthusiastic and informative session. And I would like to thank all of you. Then please attend the fill the feedback form which is posted on chat box.